Hello.
Yeah, good morning, sir. Yeah, sir, am I audible?
Just a minute. Huh?
Yes.
Hello.
Yeah, sir.
Yeah, am I audible?
Yes, you are.
Okay.
Two devices, sir. So just please mute one.
Yeah.
Yeah.
Hello.
Yes.
Yeah, is it okay now?
Yeah, it's okay, sir.
Okay.
Yeah, we'll just wait for 2-3 minutes, sir. So we'll
No issues.
strictly start at 11:05.
Yeah.
Vinesh, sir, make sirs both account as a co-host. Okay, sir.
Yes, sir, I made it.
Yeah. Okay, we will start, sir. Whether madam is there?
Yes, sir.
Yeah, can we start, ma'am?
Yeah.
Yeah, very good morning, one and all. First of all, I welcome to our today's expert, Professor Radharaman Shah, sir. I would like to introduce about him. So,
Viresh sir, start recording.
Assistant Professor and Controller of Examination at Tulsiramji Gaikwad Patil College of Engineering and Technology, Nagpur, which is autonomous institution. Sir is currently pursuing his PhD in a repowering of wind farms in India, and also he has completed his MTech from RTMNU in 2012. Sir has also worked as a senior research analyst as well as a customer engineer in MNC, that is HCL Infosystem company. As well as sir has published many papers in the area of renewable energy sources as well as power system, electricity market, as well as policies of generation. So today sir is here to share his technical knowledge on the topic of sizing of array output for the matching inverter. And I hope that session, that talk will be going to very useful for our second year, third year, and final year students. So I request to Radharaman sir to take charge and guide our students in this respect.
Hello.
Yeah,
Am I audible, Anil?
yeah, you are audible, sir.
Okay, thank you so much, Anil, for such a nice introduction. Whatever like I have gained in the industry and something related to the research area after joining this teaching profession, that I'll be sharing with the students. So which language would be preferable for the student? English, Hindi,
Yeah,
mix?
English will be great, sir.
Okay, fine.
Yeah.
So let me share my screen.
Yeah, Viresh sir, you please stop sharing so sir can share.
Yes, sir. Just a minute.
Yeah, please, sir, you can
Yes,
share.
sir. You can share now.
Okay, so is the screen visible?
Yes, sir.
Yes, sir.
Okay, let me make the, yeah. Is it okay, Anil?
Yeah, it is okay, sir.
Okay. So thank you
Sir,
so
actually, it is not as a full screen. It's showing in a PowerPoint. Can you please make a slideshow so it
I
will
have
be
made it.
properly visible?
Is it okay now?
No, that your PowerPoint windows are seeing.
I have made it.
You can reshare, and while you are resharing, that time you share the slideshow of presentation.
Just a minute.
Left, left.
Okay, is it okay now?
Just a second. Yeah, same screen is there.
I don't know what is the issue because
No, no, actually, you have done slideshow, right?
yeah.
Yeah, so while sharing that time just select that slideshow window. Slideshow window.
Okay.
Yeah, that is why it is not seeing here.
Okay, okay. Let me share it once
Yeah.
again. While sharing, it's showing.
Yeah, there may be a PowerPoint. That slideshow window is there, na?
No, only one screen is there.
Yeah, yeah. Now it is fine, sir.
Now it is okay.
Yes, yes, yes.
Is it full screen now?
Yes, yes, yes.
Okay. So
Yeah.
shall I proceed?
Yeah, yeah, sure, sir.
Okay. So thank you for inviting me for the session on the matching the array output with the inverters. This is a like a broader section of the connectivity issues with the grid in the solar PV system. What I am being like conveyed is second year, third year, as well as final year students are here. So I'll be trying to make this particular session a bit comfortable to all the participants of this particular second year, third year, as well as final year. So when we talk about the solar PV system, a lot of things come to our mind related to the grid connectivity. Why is it so? Because we know that the output from the solar PV system is in DC, and it's okay for running the DC loads, but we know that most of our loads are in AC form. So whenever like we have the solar PV system, we need to actually convert this DC power into the AC system. Then it's actually usable for the consumers. So while doing so, yes, is there any problem? Is there any issue, Anil?
No, no,
No, no,
no
sir. No,
issues,
sir. You
sir.
can continue.
Viresh, sir, you just make all mute. Only allowed to co-host to speak. Whenever there will be a question answer session, at that time we'll allow to speak others.
Okay, and one more thing, in any part, if the sound is not clear or things are not getting clear, please let me know so that I can resolve the issue from my end. Okay,
Yeah,
Anil?
yeah, sure, 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 sir. Now I'm muting all the participants. So yeah, now you can unmute yourself, sir. So others will just whenever they want to ask a questions, I will allow them to speak.
Yeah, okay.
Yeah, please
So is it
continue.
okay? Am I
Yes,
audible?
yes.
Okay. So as we all know that whatever like we do, we have to get some outcomes. So these are the outcomes that we will be achieving from today's session. The learning outcome number one is that we would be able to analyze the grid connectivity issues in the solar PV system. At the same time, we can justify the need of the improving power quality issues in the solar PV system. And finally, we will be able to design the solar PV system by optimizing the sizing of the array output to match the inverter inputs. So the third outcome is of very much importance to us in this today's session, because in today's session we will be actually knowing how to optimize the array output from the modules to match the inverter inputs. Before starting, let us make a clear understanding that nowadays we have a lot of softwares available with us. In this solar system designing, we have the softwares like PVSys, then PV Sol, and many other softwares have emerged. But if we really are not conversant with the terminologies, with the concepts which are required as an input to these softwares, then we cannot handle this software, or if at all we give wrong inputs to the arrays, wrong inputs to this software, we will land up to a problematic situation wherein we will get the wrong results, which actually is not desirable. So that's why we have to know the basics of the system design, so that we can give the proper inputs to this software. And at the same time, if we have started a small venture, like no companies will be a big company at a very short span, right? So if the company has started with a small capital, and if they don't have many customers, then this softwares would not be feasible to option for this uh, businessman. So at that time they can have this calculations available with them, and they can properly design their systems. So these would be the contents of our today's session. First, we will have a look on the schematic of the grid connected PV system, then connectivity of the to the grid or for the rooftop PV system, then the power quality issues in the solar PV system. Here, I would be specifically taking a case study of the power factor in the solar PV system with the help of some facts and figures. Then the mitigation issues, and finally the core part of our today's session, that is the matching of the array output to the voltage specifications of the inverter. We would also touch some of the parts of the MPPT tracking, and complete case study with data sheet of a solar PV module with the system. And finally, if the time permits, I will take a quick example related to the efficiency calculation of the system and the performance benchmarking of the solar PV system. Last part, if the time permits, then I would be completing. Otherwise, the main agenda or the main topic of today's session would be to match the array output to the voltage specifications of an inverter. So moving on to the schematic of a grid connected PV system. So this is how the schematic of a grid connected system looks like of a PV system, or we can say the single line diagram of the grid connected PV system would look in this way. So here we have like you can see here, these are the arrays. These are connected in series and parallel combinations. This is as per the requirement of the system and the inverter to which we are going to connect. What are the specifications of that inverter? And with the help of that, we will be then framing our PV generator system. And with that, in that way, we will be connecting the series and the parallel combinations of the PV modules. So this we will see in detail with the help of data sheets and the calculation parts in the subsequent slides. Then we have the DC switch disconnector. Then there would be, of course, inverter. Without inverter, as we have already said, that we cannot, if the loads are DC, then it's fine, but mostly we have the AC loads available with us. So we have to connect the inverter to our system. Then the AC switch disconnector, then the measuring, of course, we have the net metering, gross metering kind of availability as of now. If we have the rooftop systems, and if the systems are not rooftop, if it's the multi-megawatt system, then directly it would be connected to the grid with the substations like 11 kV or 33 kV, and depending on the output of the system, it would be even more to the 66 kV as well. So then we have the switchboard of protection devices, and finally, the main protection and the transformer, which would be connected to our substation. So this is the schematic of a grid connected PV system. Then if we talk about the connectivity of the rooftop to the PV system, we have these three schemas available with us. The first one is the standalone PV system. The second one is the grid connected PV system. And the third one is the hybrid kind of system, wherein we will have the battery backup arrangements with us. In a standalone system, our system is having standalone inverters with the batteries. it is not connected to the distribution grid, or in other ways, or in other words, we can say it is isolated from the distribution grid. In case of the grid connected PV system, it's directly connected to the distribution grid, and it uses the inverters. It doesn't have any batteries. Uh, if we want to improve the reliability of the system, like if we don't have the grid available with us, because we know that if we are having the grid connected PV system, naturally the inverter will require a reference sine wave to mimic and to get connected to the grid. But if in case the grid is unavailable, whatever generation that we are generating from this PV system, it would not be of any use to us, or in other words, we cannot use it unless and until we have the switchover kind of arrangements or the hybrid PV system kind of arrangements available with us. So in this hybrid PV kind of system, the system would be connected to the grid. At the same time, it would also have a battery backup, so that whenever the grid is not available with us, we can make use of the battery backup arrangements which we have connected to our system. So these are the three types of the connectivity schemas which are available with the grid connected rooftop PV system. Then if we talk about the interconnections, these are the ranges or the capacity of the with the capacity of the PV system, the voltage ranges which are actually given by the Central Electricity Authority India. So as per the Central Authority Electricity India, the grid connected PV systems, the capacity, if it's less than 4 kilowatt, the voltage range will be 240 volt AC single phase 50 hertz. Similarly, if the capacity is 4 kilowatt to 50 kilowatt, it would be connected to a three-phase system. And if it is more than 50 kilowatts but less than 1 megawatt, it would be connected to a 11 kV system, of course, three-phase supply. And if it's above 1 megawatt, it would then be qualified for the 33 kV transmission system. So again, these are governed by the regulations of the respective states. So like in the Maharashtra state, the DISCOMs which are available, or the Maharashtra state regulatory commissions will govern this particular scenario, and they will give us the exact nomenclature. Of course, it would be like assisting with the help of the Central Electricity Authorities rules which are given by the Government of India. Now, as I have said that we will share a power quality issue related to the power factor in the solar PV system. Now we know that in solar PV system, we are generating only active power. So reactive power is not available in the solar PV system. Whereas in the conventional grid, with uh, with the AC power. Hello. Hello, am I audible?
Yes, sir, you are audible, but your screen is off.
Screen is off. I don't know how it got stopped. I'll share it once again. Just
Okay, okay, sir. No.
yeah. Is it okay now?
Okay, sir, but can you make it full screen?
Yeah, actually, I have made it full screen itself, but I don't know. Is it okay now? Hello?
Same issue, sir.
Same issue. Okay. Just give me a moment.
Okay, no issue.
I don't know why is it happening in that way.
Hello, any issue, sir?
Yeah, actually, the screen is not coming in full screen, because here in my screen it's showing full screen,
No,
but
no, no. What you do, sir? Before sharing, you just make a slideshow.
before sharing.
Before sharing, you make slideshow, and after that, you click on share. Then you will get the full screen. So that you share here. No, no, same PowerPoint is there again. Instead of sharing PowerPoint, you can also share a full screen, sir, a whole screen if you don't mind, so that it will be there.
Uh, Sir,
Yes.
screen is totally off, sir.
Okay, okay. Just a minute. I think he's facing some issues, sir.
Okay, okay.
Sir, am I audible? Can you share this PPT with me so I can share?
Just wait, sir. Sir has left from the meeting.
Here.
Yes, please, sir.
Yeah, really, I regret the inconvenience. I don't know. Somehow there was some issues. Okay, so we were like in the power factor related issue in the solar PV module system. So as we know that solar PV system, it actually generates the active power. However, our system in the conventional grid, we do get the reactive power as well. So because of this issue, like as in the previous slide, we have seen the three types of the schemas which are available with us for the solar PV system. The first one was the standalone system, the second one grid connected system, and the third one was a hybrid system. So in the second system, like in the second part when we have started, so in the second part, that is the grid connected system, our system will be connected to the substations or the distribution grids, and these distribution grids do have the reactive powers with them right from the generation stations. But when we consider the solar PV system, it generates only the active power, because of which the reactive power is not available in the solar PV system. Now, because of this, what happens and what are the mitigation issues that we will see in the upcoming slides. This can be a project for the BE final year students or the pre-final year students as well. They can take the live project as well, like they can go with the help of the PV system module, and they can size the capacitor load banks accordingly. Anil sir, is it okay? Am I audible?
Yes, yes, you are audible, sir.
Okay. Please
Perfectly
move to the
audible,
next.
sir. No problem.
Yeah. Please move to the next slide. So
Good, good.
with the help of the case study right now, we will see how this actual system works. So here in this example, you will see that this is a conventional system. In this conventional system, what do we have is in left hand side, you will see a power grid. Right hand side, you will see the consumer, and in the center part, you will actually find the analysis of the power factor. So here in this case, what is happening is our system is having the power factor of 0.912. Like what we have taken the case study here is that the premises here the premises is having the 1000 kilowatt uh, load, and out of this 1000 kilowatt, you can see here uh, the reactive power which the system is drawing from the conventional grid, that is 450, and the calculation that is the real power is 1000 kilowatt, and the power factor is 0.912. Now let us analyze a situation if this customer wants to install a solar PV system, or in other words, if the customer wants to actually complete the partial or the customer wants to have the fulfillment of the partial load with the help of the solar PV system, then what will be the scenario? We will see in the next slide then. So now let us see that the customer has installed a solar PV system here, and the solar PV system here is generating 500 kilowatt, and the 500 kilowatt is being fulfilled by the conventional grid or the utility grid through which it is connected. But then the kVAR which it is going to draw, that would be the same, that is 450 kVAR. Because of this, like 500 and here 500, the real power here is changing, because in the previous scenario, the real power was 1000 kilowatt. However, here now the real power is 500 kilowatt. So here the power factor is changing, and the power factor has changed to 0.743. Please move to the next slide. So this is what we can understand the problem, right? So this is the problem which we actually face with the solar PV system, rooftop PV systems, because here the power factor is going to change. Now what is the solution for that? The solution for this is to size the optimum capacity of the capacitor banks, which can be installed in this system, so that our power factor issue is getting cleared. Okay, so this is one of the power factor related problem related to the solar PV system and the mitigation issues as well. So the final year student can take this as a case study with the actual loads and the with actual facts and figures. They can size the optimum capacitor bank for a client. Please move to the next slide. This is what we realize with the mitigation of these issues. Like we are majorly concerned with the voltage, current, and the power issues. See here, what we need to understand is the local requirement, or what is the local operating conditions. And with the help of this local operating conditions, we have to actually ensure that our array and the inverters, they are properly matched, and so that the designer is assured about the power which is actually expected from that solar PV system. Next. So in the coming slides, we will be understanding what is the role of maximum power point tracking controllers. So MPPT controllers, these are the controllers which are almost all the inverters are having. The all Mostly the inverters will have the MPPT range controllers, and what actually the role of this controllers is, that we will understand with the help of this. So depending on this manufacturer range, we will be having the MPPT voltage range, MPP, that is the maximum power point range, inverter operating window, and the operating voltage window or the similar terms for this particular MPPT range. Next. So uh, here I have given actually the inverters like IG15 and IG20. These are the models of the inverter, Fronius IG inverters, and the specifications which are given with this inverters. Basically, whenever we size our system or whenever we design our system, we need to understand what are the components of the system and what is the availability of the various components in the industry. So whenever we are like citing the components and the industrial requirement, we need to match both the requirements so that both the parameters, whatever data sheets that are given with this components, they are balanced and we can size our system accordingly. So we will have a case study related to this and we will understand. Next, please. Uh, this curve just I have inserted so that you can understand the relationship of the VI characteristic, that is the VOC and ISC of the solar PV module, and at the same time the power characteristics with the irradiance which is available in that particular site. In the bottom with the color code, you will be seeing the blue, red, yellow, purple. All this are showing the watt per meter square irradiance which is available in that particular area and the PV curve according to that. Here we need to understand that we are majorly focused on the irradiance part, not the temperature part. In the next slide, we will be understanding how the temperature affects the output of this from this particular module. Next, please. Yes. So this formula is very important. All the students, you can note down this formula. I'll explain this formula, what exactly this formula will help you to know what would be the output from a particular module at a given temperature. So V at X degree Celsius is equal to V at STC. STC means the standard test conditions for which that module is being tested before it reaches to the clients. Minus in the square bracket, you will find rho V. Rho V is nothing but the temperature coefficient. So this rho V would be specified by the module manufacturing companies. So whenever they test their modules in the factory and they come to the parameters, they will give this all data sheet at the backside of the solar PV module. From there, you can take these values. So multiplied by T at X degree Celsius minus T at STC. So how this formula will be used and how we can draw conclusions, we will see in the next slide with the help of a small problem. So in the next slide, we will see a small problem and we will see how the voltage changes with the changes in the temperature. Next, please. Previous slide. I hope there was, okay. Next. Okay, I think the problem will come after some 2-3 slides. So before that, we will quickly explain the concept of this MPPT controller. So here you can see that we have taken suppose a PV module, and in the previous slide, as we have seen the um, like model of the inverter, and with the optimum selection of this model, we have to be there into the MPPT range. So in the first figure that you will see here, the MPPT range is 224 to 480 volt. With the series combinations of say certain modules, if 8 modules are being connected, the lower part is not achieved, that the lower part is coming to the 205 volt and the upper limit is 324 volt. So the lower limit 205, it's falling below the lower limit of the prescribed MPPT range of that particular inverter. So that is not advisable, because if it falls below the MPPT range, it will stop working or it will fall out of sync. So that is not advisable. At the same time, the higher side, that is 324 volt, it is underutilized because the higher side is 480 volt. However, here we can see that it is coming to just 324 volt. So 8 modules is not advisable. Next, please. In next slide, you can see if we go with the 10 modules, then the lower limit is okay, but the higher limit is exceeding above the 480 volt. So again, it is not advisable. So the selection would be 9 modules. But this is like trial and error basis, or we can say in layman's language, or if the technician is not actually skilled enough, this type of calculations is okay. But if we have a detailed engineering calculations available with us, we can more precisely look into this matter, and we can more effectively size our system. This is okay if we have only 9, 8 or 10 modules with us. But if we have a multi-megawatt system, if our system capacity is increasing with a very high amount, this type of trial and error basis calculation cannot help us, right? So that's why we need to work out detailed calculations related to this, and to come up to a conclusions that what should be the optimum sizing of our system. Next, please. So that we will see with the help of the complete case study. So yes, this is the utilization of the formula that we have seen just now. So previously we have seen the formula that P at x degree Celsius is equal to V at STC minus then square bracket, and the complete formula that you all have noted down. So this we can compute with the help of this particular small example. So the example goes in this way. A PV module has a VMP of 35.4 volt and a VMP temperature coefficient of 0.16 volt per degree Celsius. So what is the VMP of the module at 55 degrees Celsius? This is our question. So these are the steps. You can see the calculation steps. In step number 1, what we will do is we will calculate the difference between the cell temperature and the STC. So the cell temperature which is given to us is 55 degrees Celsius, and the standard testing condition, that is 25 degrees Celsius. So we get 30 degree as the difference between the cell temperature, that is the actual temperature which would be available over the cell, and the standard temperature, that is the 25 degrees Celsius. So we computed first step as 30 degrees Celsius. Now we need to multiply the rho V. So rho V here is 0.16 volt per degree Celsius. So if we multiply this here 0.16 per degree Celsius, we will get 4.8 volt. So this 4.8 volt is to be taken away from the VMP of this particular module, which is available with us in the data sheet of that particular solar PV module. So 35.4 volt is the VMP which is given to us. And if we take away 4.8 volt, we get 30.6 volt, which would be the actual output of that particular PV module at the if the cell temperature reaches to 55 degrees Celsius. So you can see here the VMP was 35.4. However, we have got the result as 30.6 volt from that particular module if the temperature of the module is increased to 55 degrees Celsius with respect to the STC, that is 25 degrees Celsius. So here what conclusion that we make here is that even though our VMP is 35.4 volt, the answer that we got, the actual output from that particular site, if the cell temperature is 55 degrees Celsius, it would fall to 30.6 volt. Now, if we are arranging the number of modules in series, then we need to take the effective combination of the voltage accordingly, so that our inverter is input of the inverter can be optimized. So is it okay if at this point anyone is having any confusion? I request if anyone want to share the question, they can share the question, so that in the next part we will be able to have a detailed calculation. So am I audible, Anil sir?
Yes, yes, you are audible. And the students, if you have questions, you can raise your queries in chat box. Also, you can raise your hands. So
Yeah,
sir
so
can
that
answer that every question end of the session.
chat box questions can be then taken. So because this is a very important calculation, because most of the times what we are under the impression is that in the summer season we will get the maximum output from the solar PV system. But this is not the case. In summer season, the temperature coefficient effect is at the maximum part, and because of that, we need to size our system accordingly so that our system is not oversized as well as our system is not undersized as well. So this part is very much important. We need to understand this part. With the irradiance, if the temperature coefficient is also increasing, then there would be naturally the impact of that in the VOC, that is the uh, open circuit voltage of the PV modules. So shall we proceed ahead?
Yes, sir. Yes, please.
Okay, please move to the next slide. Then we will quickly take the case study and we will know the system. So this I have this slide I have like inserted most of the times. If we start our business in the solar PV system, or if we are in a job in some company, then naturally the first point, that is the specific peak wattage PV to be installed, that is the tender requirement. So many times the companies quote tenders. So what is the requirement of the tender? What is the client's available financial budget? Physical space available for the system. So these all are the constraints which we need to consider when we size a PV array. Next, please. Similarly, the irradiation data also is of much importance to us. So I have given some site here. You can go through this site so that you can locate the particular geographical location of that particular site, and you can get the details of the solar irradiation data which is available. At the same time, there are some specialized programs like PVSys, PVSol, etc., from where also we can get the uh, details and we can size our system accordingly. Even we can do the shadow analysis, and many features are there in this PV system. So if the students want to download the demo copy is available in the PVSys website. The demo copy works for 1 month. So in the 1 month, you can take your hands on and you can try it at your end so that you can after 1 month it will be expired, so you will have to log in from the other account. Next, please. In the next, like here, we start our core topic of our today's session, that is the complete sizing of the inverter and the module array. So these are the steps we need to, which we need to follow, and at the end of the fourth step, we would be able to design the optimized match of the array output to the inverter input. So the quickly steps I'll go through. The first is minimum number of modules which should be there per string. Second step is maximum number of PV module per string. Third step is maximum number of strings. Fourth step is total maximum number of modules. So with this four steps, we will be actually calculating manually, because see, I have said that there are softwares which are available. So we need to handle the software. We need to give the inputs to the software so that we get the actual result which is expected from that particular exercise. So we will start with the first step, that is the minimum number of PV modules per string. Next, please. Before that, we will take the problem statement. In the next slide, we will have the problem statement. Next slide, please. Okay, so this is our problem statement. So here the problem statement which we are identifying is that how many Suntech Pluto 205 ADE solar modules. So Suntech Pluto 205 AD, this is the model of our solar PV module. Would you connect to a Frownius IG60 inverter? How would these modules be configured? That is, determine the number of modules in each string and number of string. The maximum effective cell temperature recorded at the site is 75 degrees Celsius. See, we need to be very clear that what would be the maximum cell temperature in that particular site. Because if we are designing a system for, let's say, a very a typical area, Jammu and Kashmir, and if we are designing a system for a Rajasthan-based plant, so naturally the ambient conditions, the temperature range in both the site would be different. And with the temperature range, as we have seen in the previous slide, the formula and the actual calculation, the VOC output from that particular module will also change. the same module, the same make, the same company and the same systems, if you install at a two different sites, the output from both the sites would differ from each other, because the climatic conditions in both the sites would not be the same. So this needs to be taken into consideration while actually designing the system. So here the complete characteristics of the nameplate rating that I have talked upon, that the nameplate rating would be available with you at the backside of the PV module. From there you can take it out. So I'll not go in much detail here. In the numerical, we will go through the detailed content. Next slide, please. Uh, in the next slide, you will be having the other characteristics, like we have to get the rho V, which was there in the formula. So rho V, we need to take into effect. So here we have the rho V of Pmax, VOC, ISC. So all these three temperature coefficients are available with us. At the same time, we are also being supplied with the inverter specifications, which are given on the screen. So students, you can note it down. You can take a screenshot of it if you want, so that we can take this numerical quickly. Otherwise, it will consume more time. Next, please. Okay, so here we start with our first step, that is to calculate the minimum number of PV modules which are to be there in a string. So number of strings, such strings would be there in the system. So we will calculate one by one. So first part of this step number one, that is calculate the temperature difference, as we did in the previous numerical. So here the maximum cell temperature that would be there in the site, it's available with us, that is 75 degrees Celsius. So we would take away 75 with the STC, that is 25, which would give us 50 degrees Celsius. Now, the Pmax coefficient, which was given to us, which was in the form of percentage per degree Celsius, we are converting it to the volt per degree Celsius. So how we convert it is given on the screen. 0.38% per degree Celsius multiplied by 38.1, which was already available with us, VMP. So 38.1 multiplied, it would give us 0.145 volt per degree Celsius. So this is our rho V, which we will be using in our formula, which we have seen a short while back. Then multiply this rho V with the temperature difference, that is 50 degrees Celsius. So we get 7.25. So that is 50 degrees Celsius multiplied by 0.145 volt per degree Celsius. So we get 7.25 volt. Now, we would take away this 7.25 from 38.1, which was the VMP, which was given to us. So we get 30.85 volt. Now, we need to take into account 2% voltage drop for the safety margin. So we will multiply this with 0.98 and we get 30.2 volt. So this 30.2 volt would be the actual output from that particular site if the cell temperature reaches to its maximum, that is 75 degrees Celsius. So we need to take into consideration maximum cell temperature. Right. Hello, am I audible?
Yes, you are audible, sir.
Okay, please move to the next slide. So then we will calculate the minimum number of modules with the help of this set of next formulas, that is multiply the safety margin of 10% with the inverter's minimum voltage range. So inverter's minimum voltage range was given as 150 volt as per the data sheet provided to us of the inverter. So we will multiply this 10% safety margin. I have taken this 10% as a standard safety margin, which is generally considered in the installations, commercial installations. So I have taken 10% safety margin. So this would be 165 volt. So we would not go below 165 volt, even though our voltage range of the inverter was given as lower limit was given as 150 volt, but we would not reach up to 150. We would, as for a safety margin, we would consider it as a 165 volt. So in order to get the number of modules, we would divide this 165 volt with the VOC output, which would actually be available with us if in case the site voltage, site temperature reaches the maximum, that is cell temperature, not the site temperature, is the cell temperature. So 30.2, so we get 5.46. We would round up this 5.46, so we get 6 number of modules which would be available with us with the requirements of the PV modules, the data specifications which was given to us of the PV module. We would be connecting such modules, 6 modules in series, minimum number of modules. So this would be the minimum number of modules available with us. Okay, so this is the first step which we have completed to calculate the minimum number of PV modules which are to be connected in series for the particular specifications in the problem statement which was given to us. Next, please. Next, we will calculate the maximum number of modules. So as we have calculated the minimum number of modules, now we need to calculate the maximum number of modules which needs to be connected in series for the problem statement which we have seen here. So for this, what we would do in extreme cases, the 0 degree Celsius is taken here as the minimum temperature which was given in the problem statement. So I have taken here 0 degree Celsius. So the temperature difference comes to minus 25 degrees Celsius. Here, while considering the maximum number of modules, when we are going to the minimum cell temperature that would be available with us, we take here the temperature coefficient of VOC, and as it was given in percentage per degree Celsius, we need to convert it in volt per degree Celsius, because everything is in volt. So we are going to convert it in volt per degree Celsius. So we multiply this with the 45.8 volt VOC which was provided to us in the data sheet. So VOC multiplied by the VOC coefficient, that gives us 0.133 volt per degree Celsius. Then we will multiply this with 25 degrees Celsius and we will add this. So you can see here, as the temperature difference comes negative, we are adding up here and it would ultimately give us the voltage output, VOC output, if the temperature falls to 0 degree Celsius and the cell temperature reaches to minus 25 degrees Celsius, we would have 49.12 volt, which would be the output from that particular PV module. Next, please. So this is the maximum output that we will see here. And again, the as we are considering here the maximum part, so no voltage drop we are looking over here, because we need to calculate the maximum number of modules. So we will take it as it is, that is 49.12 volt. Now we need to, as we are moving to the maximum part, so we need to have the higher limit of the inverter voltage that is given to us, that is 500 volt. But as we all know that we cannot reach exactly to the higher limit, we have to margin us to some safety limit. So I have taken the safety margin as 5%, and if I take the safety margin as 5%, it would be 475 volt. So the minimum which was given to us was 150 volt. We have taken the safety margin and we had considered it as 165 volt. Now the higher limit was given is given as 500, but we will not reach 500. We will limit ourselves to 475 volt. So here, if we are calculating the maximum number of modules, we need to again do the same exercise. That is the VOC divided by the inverter voltage range divided by the VOC, that would give us 9.67. And as we are calculating the maximum number of modules, we would round down here. So 9.67 would be round down here, not up here, because already we are reaching to the maximum limit. So we would round down here and the maximum number of modules would be 9 modules per string. So here with step number 1 and step number 2, we can conclude that for the given system, for the given problem statement with the set of instructions available to us, we can employ 6 to 9 modules. So in a string, so 6 to 9 modules in a string would be a range available with us. But if you look at from the perspective of the businessman, you need to have the customer satisfaction at one end. At the same time, you need to earn more profits from your project at the second end. Third point, you cannot downgrade your system, because if you downgrade your system, what you will have is less output from the system. Again, the customer is going to complain to you that I have got the less output from the system. At the same time, if you are quoting a tender for a government site or something like that, then again, the output from this particular system is a matter of concern. That's why the optimum selection between 6 to 9 is very much important. So this we will see with the help of the step number 3 and step number 4. So let us go to the step number 3 in next slide. Next slide. Yeah. So in this next slide, maximum number of strings. So for the maximum number of strings, we are given the operating current window for the inverter as 0 to 35.84 ampere DC. And at the same time, the ISC of a module is given as the 5.73 ampere. So 5.73 is the short circuit current of a single module. And at the max, the operating current for the inverter is 35.84. So if we divide this 35.84 by 5.73, that is the ISC, we get the value which is 6.25. Again, if we round down, so this would be the maximum number of strings which are needed to be connected in parallel, because we have the size of our system available with us. In the step number 4, you will see the total maximum number of modules which are to be inserted here. So here, if you go with the maximum number of modules, you can see here from the calculations of step number 1 and step number 2, the maximum number of modules for this given problem statement would be 9. Minimum number of modules for this given problem statement would be 6. And at the same time, the rating of one single module which is given in this particular problem statement is 205 watt. So 9 multiplied by 5 would give you 54 modules. 54 modules multiplied by 205 would give you 11070 watt. But the inverter rating which is provided to us is 6700 watt. So this is the disconnect here, that step number 1, step number 2, step number 3 is fine, no issues. We have calculated the minimum, we have calculated the maximum, we have as well calculated what should be the maximum number of strings which are to be connected in parallel, because we know that in series voltage would get add up and in parallel the current would get add up. So if we want to increase the current, we need to arrange the system in parallel. If we need to build up the voltage, we need to connect the system in series. So naturally, the series and parallel combinations would be required by us, right? But how many such strings should be there? What should be the optimum number of things? These are the points which we need to actually calculate, looking towards the site consideration, looking towards the requirement of the customer, looking towards the requirement of the system. Next, please. In the next slide, then we will see how actually we then optimize this particular system. So here you can see in the first column number of string I have inserted. In the second column modules per string. In the third column modules, it would be the total number of modules. It's please correct it here. That would be the total number of modules. So in the first column you can see here number of strings. So whatever calculations that we have done in the step number 1, 2, 3 and 4, we have come to a conclusion that the number of strings cannot be more than 6, right? So that's why that is the reason which I have taken here 4, 5, 4, 3, 4. So these are the combinations which I have taken here. And in the next column, you will see modules per string. So in the modules per string, again, you can see here that we have taken the minimum number of modules as 6, maximum number of modules as 9. So we have taken a combination 8, 6, 7, 9, 6, so that we come to the total number of modules. So if you multiply column 1 with column 2, you will get the column 3. So in the first column, that is 8 multiplied by 4 is 32. Second column, 5 multiplied by 6 is 30. Third, 4 multiplied by 7 is 28. 3 multiplied by 9 is 27. And 4 multiplied by 6 is 24. Similarly, if you will multiply the third column with 205, why 205? 205 is the rating of one module which was given to us in the problem statement. So in the problem statement, 205 watt was given for a single module. So if I multiply 32 with 205, I will get 6560. If I multiply 30 with 205, I'll get 6150. If I multiply 28 with 205, I'll get 5740, and so on. 24 multiplied by 205, I'll get 4920. So this complete thing which we have done manually, this can be done with the help of the softwares which we have seen in the previous slides, that is PVSys, PVSol, and other customized softwares available with us. But if we don't know the exact calculation part, if we don't know the philosophy behind the sizing part, if we don't know the exact specifications of all these parts, we would land up into a trouble and we would not be able to handle the software effectively. As a result of it, the software will give a wrong output to us and we will end up with a wrong sizing of the system. So from this table, what we can conclude here is, as the inverter size which is provided to us is having 6700 watt, or in other words 6.7 kilowatt, the first sizing that is highlighted with the yellow color, that is 4 number of strings, maximum number of modules per string as 8, and total number of modules as 32. This would be the optimized selection, or this would be the optimized calculation which we would do in order to match the array output with the inverter specifications. So this was the part which was the core part of our today's expert session, and I hope I am being able to convey the calculation part and to solve the particular problem statement. I have just taken a problem statement with the help of the data sheet which is available from the solar PV module manufacturers as well as the inverter manufacturers. You can take such problems with you as a project. You can size your system as a project, because see, again, these are the ideal calculations. When you will go to a particular site, you will um, check the rooftop size of your client, because every time your rooftop size would not be even, right? Even in the sense, it would not be square, it would not be rectangle, sometimes it would have some altogether different shape, right? So in that case, you should be in a position to justify your requirement of the client, and you should be able to actually size your system according to the requirement of the client. At the same time, what are the tender specifications? If you are quoting a government tender, if you are entering into a business or something like that, then you need to consider those parts as well. So I'll give a pause here. If there is any questions related to this, we can take it in the next part quickly. Then I'll take the performance efficiency and the other details. So Anil sir, over to you.
Yeah. If any questions, please students can ask. Shreyash, Prashant Siraskar, if any questions, you can ask to sirs. Just raise your hand if you want to ask a question. Sir will unmute you.
Okay, please move to the next slide then. Till the time questions comes, and if there are questions at all, we will take it at the end. Then we will next. If you will look at the efficiency of the system or the energy yield calculation, this is a brief calculation part, which with the help of which you can actually calculate the efficiency and the energy yield of your system. So energy yield of the system is given by the irradiation multiplied by the module rated power multiplied by the losses. So here first two blocks, that is the irradiation and the module rated power, this is okay because this would be available with us. For a particular site, we would be knowing the irradiation. There are n number of sources from where we can get this irradiation of that particular site. Module rated power also would be available with us with the nameplate rating. What we need to calculate is the losses from that particular system. Next, please. So losses are categorized in various parts. So we will have a quick exercise or a short numerical, and with the help of that, we will actually understand how these losses are taken into effect, or how these losses are considered in order to model a system. So here I have taken a system with 65 multiplied by 175 modules and a Frownius IG60 inverter, which has just been installed. And what would be the annual energy yield? These are the specifications which is given to us. Daily average irradiation is given as 4.5 peak sunshine hours, shading losses as 5%, voltage drop as 2%, dirt loss as 6%, and design ambient temperature is 23 degrees Celsius. Information has been taken directly from the manufacturer's datasheet. Pmax is taken as 175 watt. Temperature coefficient of Pmax is given as point, and the various specifications are over the screen. With the help of this, we are going to calculate the energy yield from this particular site. Next, please. So here you can see the calculation losses, because as I have said that first two blocks are okay, because we can get this data from the sources. What we need to focus upon is the losses. So in this particular table, you can see I have calculated the losses. The first part is the cell temperature, then the temperature difference and temperature coefficient, the losses from it. I have calculated it. You can see here, multiply the temperature coefficient by temperature difference, that would give you 0.115, and from here you can calculate the loss due to the temperature. So the temperature effect you can consider, and 0.885 would be the loss effect due to the temperature. Next, please. Similarly, the various other type of the losses, that is the shading, voltage drop, dirt, temperature we have already calculated just now. Inverter efficiency, manufacturer tolerance. So the amount of losses which was given to us, we have multiplied it with the appropriate factors, and we have calculated it as shading losses as 0.95 factor, voltage drop as 0.98, dirt as 0.94, temperature as 0.885, inverter as 0.943, manufacturer tolerance as 0.94, and the cumulative of all these losses would effect as the 0.708. So if you multiply this, you will get the exact energy yield which will be there from that particular system round the year, that is 6516 kilowatt hour per year, or in other words 6516 units from that particular system. Next, please. So with this example, you can come to the exact energy which can be calculated from that particular system. Next is specific energy yield. So this is the parameter which is required for the performance comparisons of the system. So which this is given by the system annual average energy yield divided by the installed rated PV array power. Next, please. So we will again have a quick example, and we will understand this concept of the specific energy yield. Next slide, please. So as I said that performance ratio, and in the last case study also I have said that if you have two different sites like in Jammu Kashmir and say Rajasthan, or in any other parts of our country, or for that matter in any part of the world, with the same specification, with the same inverter, make everything if you keep same, but still if you want to compare the performance of one system with the other, you can very well compare it with the help of the technical specifications, or the data which is available with us. At the same time, the parameters for that performance, you can calculate what would be the, or which plant would be running good in comparison with the other, with the help of this performance ratio. So this performance ratio is given as system annual average energy yield divided by the theoretical maximum energy yield. So whenever we calculate the theoretical maximum energy yield, we consider that no losses are there in the system. That is the theoretical maximum energy yield, right? So with the help of this, we will calculate the performance ratio, and we will come to a conclusion that how the systems would be working with the exact number of modules available at one site, and the same number of modules, same number of inverter, everything keeping same at the other side. We will see this with the help of a example. Next, please. Okay. So this is the example available with us. So we have two identical setups of 5 kilowatt each. One is installed at Srinagar and the second one is installed at Hyderabad. Srinagar system is producing 6796 kilowatt hour per year. The Srinagar has an average daily irradiance of 4.27 peak sunshine hours and average daytime temperature of 20 degrees Celsius. With the yellow portion, you will see the second side, that is Hyderabad. We have Hyderabad system. It's also having 5 kilowatt system itself, but it's generating 8336 kilowatt hour per year. Hyderabad is having average daily irradiation of 5.65 peak sunshine hours and the average daytime temperature of 35 degrees Celsius. So how would you compare this both the sides with each other? How would you draw your own conclusions that which side is performing better in comparison with the other one? So if you will look at the number of units which is generated from this both the side. So you can see Srinagar is generating 6796 kilowatt hour per year. At the same time, Hyderabad is generating 8336 kilowatt hour per year. So being a developer, you can without any like detailed calculation, at a glance, you can say that Hyderabad may be performing at a better condition because the 5 kilowatt system is giving an output of 6796 kilowatt hour in Srinagar, but it is giving 8336 kilowatt hour in Hyderabad. So naturally, the amount matters. Amount matters in the sense 8336. If you will take at a glance, you will say that okay, my Hyderabad site is generating more number of power, so that is performing better in comparison to Srinagar. But it's not the case. We need to do the performance ratio analysis, and then we need to come to a conclusion that which site is performing better in comparison to the other one. Next slide, please. So we will calculate the performance ratio of both the sites, and then we will come to a conclusion that which one is performing better. So you can see here theoretical maximum energy yield, what we can calculate without any losses. So peak sunshine hours multiplied by the 365 days in a year multiplied by the rating of that system, that is 5 kilowatt. So this would give you 7793 kilowatt hour per year. So this would be the theoretical maximum energy yield. However, the actual energy yield which is recorded at that particular site, which is given to us, is 6797. So the performance ratio would be 6797 divided by 7793. That would give you 0.87. Fine. Next, if you calculate the same thing with Hyderabad, even though you get your system got 8336 kWh per year as the actual average energy yield, which is recorded in that particular site, but what is the theoretical maximum energy yield looking toward the peak sunshine hour of that particular site? That would give you 5.65, that is the peak sunshine hour multiplied by number of days in a year multiplied by the system, that is 5 kilowatt. This would give you the theoretical maximum energy yield as 10311 kWh per year. So if you calculate the performance ratio of Hyderabad, 8336, which is the actual one which is recorded, divided by 10311, which will give you 0.80. Now from this 0.87 and 0.80, you can very well conclude which one is performing better in comparison to the other one. So is it clear, everyone? Have you all got the like philosophy of the solar PV system design, that it's not only about the irradiance, it's about the temperature gradient factor as well. So the temperature gradient factor plays a major role in the system design of the PV modules. Whenever you consider a site, please check what would be the maximum cell temperature of that particular site and minimum temperature, and then only make your system design accordingly. I would take again a pause here. If there are a set of questions, we can take it here, because next part would be the uh, what we can say, what are the various opportunities which are available in this particular arena, which the final year students, I don't think, because they have already completed their major project, but yes, if third year students are connected here, if second year students are connected here, they can give a thought to it, and they can start their preparations accordingly, so that in a final year they would be in a better condition to take a uh, good project, in the sense, take a project which would actually give them an employment in this particular sector, because this sector is a very emerging sector, and it's at the same time, if someone wants to go for entrepreneurship, they can also give a thought to it. So Anil sir, I'll take a pause here. If there are any questions, we can quickly take it, and then we will move to the next slides.
Yeah, we can continue also, sir. If they have any questions or queries, they will put into chat box.
Okay, then we will move to the next slide. Next
Yes.
slide, please. So there are ample number of opportunities nowadays, as you all know, that artificial intelligence is the buzzwords nowadays. Artificial intelligence की बातें हर कोई कर रहा है, right? Artificial intelligence in data science, artificial intelligence, and every sector, like you can move artificial intelligence. It's not only constrained with the computer science engineering or the information technology student. Artificial intelligence is something which has to do with all the sectors of the engineering, not only engineering, in medical science, everywhere this artificial intelligence has got a application part, and the same is applicable for this particular scenario as well. So what we can do is use of artificial intelligence and data mining in the generation forecasting. So all students should know that the Central Electricity Authority has given the mandate to all the generation companies. They have to give the forecasting of their generation. So this can be done with the help of the artificial intelligence as well as the data mining. Next slide, please. There are other sides of opportunities which are there for the complete value chain of the electricity sector, right from the generation, investors, profitability, transmission, power trading, large industrial consumers, and the regulatory as well as the policy and the tariff fixation. So this is the complete chain in which the students can work upon. They can work towards their final year project, and they can choose topics related to this, which will uh, actually take the help of artificial intelligence and club all these tools with to make a effective implementation of this into a complete project. Next, please. Next slide, please. Yes. So asset monitoring, inspection, and analytics is one such area. As you all know that IoT systems are also a common words nowadays. So asset monitoring, even electric vehicles, we are talking about in the electrical engineering. So we can make use of this asset monitoring part with the help of the artificial intelligence, and we can program our systems accordingly, and we can know what actually the conditions of our assets would be. Asset in the sense, as we are into the power world, as we are into the electrical engineering, our assets are all the complete range of the generation, transmission, distribution, complete range of the utilities we can merge into, and we can make use of this with the help of the artificial intelligence tools. Similarly, as you all know that PLC, SCADA, all these things, PLC is outdated now. We have HMI interface as well nowadays. We are into the world of Industry 4.0, where we have PMU, that is Phasor Management Unit, IoT, cloud, all this can be integrated to make a workable project in your final year for the final year student. Next, please. Asset management, there are many things which can be done in the asset management. You can take a industry live project as well. In the industry, if you approach to the industry for your industrial project, you can do the inventory control for them. You can have the reliability assessment. You can also do the outages and the maintenance part, preventive and the action part. All this can be integrated with the cloud and IoT based, and similarly, with the help of the artificial intelligence sets, you can actually propose your work to the this industries for the further part. Next, please. I hope the slides are over. Yeah. So in the last slides, I have tried to give a brief like what are the projects that the students can take. Probably the second year and third year students, they can opt for it, because final year students might have already completed their major project. So here we come to the end of our today's session. I hope the learning outcomes which were given at the start of the presentation. Can we move back to the second slide? Second slide of the presentation. Can we move back? Because I am very much concerned with the outcomes, because as you all know that we are living in the outcome based education, uh, and we need to know whether really the outcomes have achieved or not. Second slide. So the first outcome which we have, first outcome was related to the previous one, please. Previous slide. Yeah, so analyze the grid connectivity issues. Second was the justify the need of improving power quality issues in the solar PV system. And the third one was to design the solar PV system by optimum sizing of the array output to match the inverter input. So I hope I am being able to map all these three outcomes which we have given at the start of the session with the help of the complete presentation. So over to you, Anil sir.
Yeah. Am I audible? Viresh sir?
Yes, sir, you are audible.
Yeah. I request all students, sir, now you can unmute all. Okay, I had done setting. Okay, no issue. Okay, now I request to students, if you have any questions, you can ask your queries to the sir. Yes, anyone from last year?
Okay, in the last slide, I have given my mail ID as well. So
Yes, sir, move to the last slide so students can note down sir's mail ID as well as
even
contact number.
I have given my contact number as well. So from my experience, if I can help anyone, I would be really happy, and I would really appreciate if anyone can connect, so that I can also learn, because we all are in a learning phase, and the learning never ends throughout our life. So at each day we learn some new things. So probably because students are the main motivators for us, and the students are the one which compel us to learn the new things, because if we don't learn the new things, the student will make us outdated, and we would be of no use to the students, because as in this today's world, everything is being online, and most of the things are available in the YouTube and many things. So the value chain for the teachers have become less. So we all teachers have to be updated, and I try myself to update with every point of time. So if any student wishes to connect with me, I have given my mail ID as well as my number, so you can connect, so that I can also learn from you.
Yeah, thank you very much, sir. Okay, I request to students, you can just note down sir's number as well as mail ID, and in future, if you are working any projects related to the contents, whatever sir had delivered, so you can ask to the sir. Okay, so I would like to request Professor Dhanraj Dafle sir. For
1
the
minute, sir.
Thanks.
1 minute.
Yeah.
Sir, can you turn on camera, please? Radharaman, sir. I will
Yeah,
take
I
it.
have turned on. I
Sir's
have
camera
turned
is
on my
on
camera.
live, sir. I'll just spotlight him. So you can stop sharing. Yeah, now it is okay. Okay, fine. So I would request to Dafle sir to give a vote of thanks for this expert talk.
Hello, Anil sir, whether I'm audible?
Yeah, you are
Yeah. Audible.
Yeah. Okay, we are at the end of session. So I'm here to propose a vote of thanks on behalf of our Sweri family. So first of all, I will thank to the speaker of our today's event, Professor Radharaman Shah sir, who has given this wonderful knowledge related to this topic. And I hope that all students got the new concept and new knowledge related to this. Okay, thank you, sir, on behalf of our Sweri family.
Thank you
Next
so
speaker,
much, sir, for inviting me to deliver
Yes, sir.
the
Yes, sir.
session. And I'm really, whatever I have like able to share more, I will be connected with you all so that we can learn more things.
Yes, sir. Yes, sir.
Yes, sir. Thank you. Actually, sir, we have two specialized persons who have done their PhD. Myself, I have done in control system, and Patil sir have done in power system. So
Good afternoon, ma'am.
good afternoon. In the renewable energy, most of the part is related to control only, so that we
Yeah.
can do something in collaboration also.
Surely, ma'am. I'll be really happy to collaborate with you because
And rather, I would like to take that privilege because on
no,
our
ma'am.
college
Yeah.
rooftop 400 kilowatt solar plant is there, and total
Okay.
system is SCADA system. So if for your PhD work, if you want that data, you can take, so that collaborative work we can go for.
Sure,
Because
ma'am.
total
Thanks
SCADA
a lot,
system
ma'am.
is there. Total SCADA system is there. Therefore, live data you can get for your research work.
Sure, ma'am.
Okay, already TK sir is in touch with you. So anytime you visit to Pandharpur to meet Lord with
Sure, ma'am.
etc.
Yes,
And in
ma'am.
that
I'll
you
take
will
him to the
start with
institute
our
also.
work also.
Yeah, we will be associated with each other.
Yeah.
And in future also how we can like collaborate, we will see to it.
Yes.
Okay.
Now at last, I'd request all students, please turn on your video so we can take one screenshot as attendance. So all the students are requested. Just turn on your cameras.
Just wait, sir.
Sir, one more thing I would like to ask.
Yes, please, sir.
Do you take a feedback of the session?
Yes. I am taking feedback
Yes.
and I will
Kindly
share with you.
do share it with me.
Yes.
Because I need to improve myself, and I really need to know which parts further improvements are required.
Yes. I will definitely share, sir. Okay, all the students are requested to turn on your cameras. Viresh sir, please at your side, you just take a.
Yes, sir. I will take.
Yes, please. Yes. So thank you very much, sir. Thank you again. And in future, as madam already discussed, in future, if it is if the requirement, will surely associate with each other. So thank you for
so
accepting
much.
our invitation, sir.
Thank you, ma'am,
I
for
would like to thank
giving
you
the
our
opportunity to
Honorable
share a
Principal
small
Dr. Deepthi Ronge, sir.
knowledge which I have gained. Thank you again.
Yeah. Thank you, sir.
Thank you, sir.
very much.
Okay, sir. Thank you.
Thank you so much, sir. Sir, can I close the session?
Yes.
Yeah.
Okay, thank you.